morning, Calculus 1. If we move into section 3.6, we do derivatives of inverse functions. Now, the book kind of generalizes that and does derivatives of all kinds of inverse functions, but I just want to focus on the trig inverse functions. Now, there is 6 of them. There's 6 trig functions, and then each one of those has an inverse trig function. I only wrote down 3 here. The derivative of arc sine of x, that's the inverse of the sine function x. It's called arc sine of x. It is this function, y equals sine inverse of x, or we write it as the arc sine of x, or maybe I don't even have to capitalize it like I didn't here, the arc sine of x. So it's the inverse function. I don't know, I want to teach you this calculus, but I feel like I got to go back and teach you a little bit about what that means. So, you know, a trig function, you plug in angles and it spits out numbers. You plug in 30 degrees, the sine of 30 degrees is 1/2. You plug in angles, it spits out numbers. The inverse trig function, you plug in the number and the answer is an angle. So the arc sine of 1/2 is 30 degrees, or pi over 6. So it's that inverse operation. Anyway, here's the new rule. So we got 6 new derivative rules to learn. I thought we were kind of finished with them. Maybe you thought you were finished with them. But the derivative of arc sine of x is this: 1 over the square root 1 minus x squared. The derivative of, you can read these, the derivative with respect to x of arc tangent of x, that's a new function, is 1 over 1 plus x squared. Notice no square root. Different pattern there. And the derivative of arc secant is 1 over the absolute value of x in front of the square root of x squared minus 1. Notice the reverse subtraction. X squared minus 1 in the square root is different than 1 minus x squared in the square root. By the way, this addition can be written either way, of course. When you're adding numbers, you can write that in either order. But this order of this subtraction is different. So there they are. Now, there is 3 other ones. There's arc cosine, arc cotangent, and arc cosecant. And it turns out that their derivative rules are these exact rules with a negative sign in front of them. So the derivative of arc cosine is this rule with a negative 1 on top. The derivative of arc cotangent, negative on top. Derivative of arc, negative on top. So that's why I only wrote down those 3. So 3 new rules, and let's just prove one of these for you. You know, if you have y equals the arc sine of x, its derivative will be this answer. I mean, so if I say y prime, the derivative is that answer. But let's prove it. So the way to prove it, the way to derive this is to, let's see, rewrite this as what it says. So y is the angle whose sine is x. The arc sine of this number x is this angle y. Or you could say, let's take the sine of both sides, and you get the sine of y equals the sine of the arc sine. Well, the sine of the arc sine, since they're inverses, they cancel each other out, and we just get x. So I'm rewriting this statement as this. These are equivalent statements. All these are equivalent statements. And now I can take this derivative, but it would have to do it implicitly. I learned how to do implicit derivatives. I can take the derivative of sine y, I think it's cosine y, times dy dx. And then I can go to the other side and take the derivative of x. It's a 1. I can solve for dy dx. dy dx is 1 over cosine y. So there's the derivative of this original function, which was this. Now, that's not the rule I wrote down. So let's see how we can go from this to that answer. And we do that by drawing a triangle. Whenever you're messing around with arc sine, arc tangent, it is an angle. And sometimes what you can do is draw a triangle for that angle. So here's what I'm saying. The arc sine of this number x is this angle y, or the sine of angle y is x. If you drew a picture of that, draw a right right triangle. The angle is y, make that your angle y. And if the sine of y is x, we know that's opposite over hypotenuse. So x over 1 is how we would label this triangle. Using Pythagorean's theorem, we can get the other leg of the triangle. It's the hypotenuse squared minus that leg squared, square rooted. That was Pythagorean's theorem, you guys. The hypotenuse squared minus that squared equals this guy squared. Or this guy squared plus this guy squared equals the hypotenuse squared. That's all true. So we found this. Now hang on. What's the cosine of angle y? What's the cosine of angle y? The cosine is the adjacent over the hypotenuse. So very quickly, I can replace this cosine of y with what it is, the adjacent over the hypotenuse. It's just the square root. So basically, I just proved to you that formula. And it's not that hard to do. Rewrite the function, take the derivative implicitly, solve for there's the derivative, but to get it in the form we want, we have to draw a triangle and see the relationship between x's and y's. So you could do that. You could do it for arctangent, you could do it for arcsecant, you could prove it to yourself. Before I quit this video, let's do an example. So if I walk into a function, y equals the arctangent, I'm sorry, hang on here. If y equals 8 times the arctangent of 2x, can you please take the derivative? Well, there's the rule, and according to that rule, I'll follow that rule. Here I go. What do you do? Oh, hang on. What do you do with a multiplied constant out front? A multiplied constant out front, we've been dealing with that. It just kind of sits there. We slip right past the multiplied constant. We pull it out front is what one way we say it. And we take the arctangent of 2x. We take the derivative of arctangent. Well, there's the rule. So it's 1 over 1 plus that argument of the function squared. So it is that 2x quantity squared. And hopefully you realize that you're not finished. You realize that in this particular situation, because it's a 2x, you need to do the chain rule. And the way I've been talking is the chain rule spits out the derivative of the 2x. The chain rule spits out a 2. So we multiply by a 2. Now when I wrote these rules, well anyway, let's finish this, sorry. I would take the 8 and the 2 and multiply them together up in the numerator, call that 16 over 1 plus, and I would go ahead and square that quantity, and that would be a 4x squared. That's awesome. That's the derivative of this function, using our new arctangent rule here. You know, when I wrote these rules, I wrote them in terms of x. I said, let's take the derivative of arctangent x. And like I just got done saying, if it's more than an x, if it's a 2x or an x squared or an e to the x, you better do the chain rule. And I think my students know that, so I feel like I can write the rule like this and they can do the chain rule. But maybe you recall earlier that once you learn the chain rule, the book and maybe some teachers, they start to write the rule like this. If I wanted to write the rule like this, I would write the derivative of arctangent of u. And I would write 1 over 1 plus u squared times u prime. I mean, that's when we write u, but we take the derivative with respect to x, we're implying that the u is a function of x. It's more than just a single x. And that implies that at the end of this problem, you have to do the derivative of the u. You have to do the chain rule. So anyway, sometimes we write our rules with a u in there, the chain rule there. I sometimes write my rules like this, and of course, you should know when to do the chain rule. So cool, here I go. That's the derivative. What is that? That's a formula for the slope of the tangent line, of course. All right, there's probably some more good problems in here, but the 3-6 to me is a few more rules here. We're almost at the end of chapter 3. We got some great word problems coming next. But we are done with derivative rules now. We really are done with derivative rules now. You've got all the 6 trig functions. Now you got the 6 inverse trig functions. You have the e function. You got his inverse, the log function. You got the power rule, the quotient rule, the product rule. That should help you with all kinds of mixtures of all that stuff. Chain rule. Yeah, you're good. I think you can take the derivative of almost anything. Practice. All right, thank you.